Particulate tool. We're going to start this session with the presentation by the title, Simulating the Stability of a Particle Embedded in Liquid Column Using a Gas Liquid Solid Three-Phase Lattice Boltzmann Model.
Okay, thank you for the introduction. And good morning, everyone. My name is Shitong Zhang. I'm from the University of Edinburgh. And today I'm going to talk about the simulating the instability of a particle embedded in a liquid column using a gas liquid solid three-phase lattice Boltzmann model. And this work was supervised by Professor Haiku Liu in Xi'an Jiaotong University. Oh, sorry. Okay, sorry. My talk mainly includes the following 5 sections. First, I will give a brief introduction about the background and motivation. And second part is about how do the capillary force in the interaction between the solid and the liquid surface. And third part is about the lattice Boltzmann model we have developed to simulate the lattice the liquid gas solid three-phase flow. And the first part is we use the developed method to simulate instability process of a liquid column with a particle at the interface. And then we come to the summary section. So why it's okay. So the liquid gas solid three-phase flow can be commonly seen in our daily life and also in nature and industry applications. And at the micro scale, the surface tension can dramatically affect the dynamics of the solid part. And for example, in the first figure, so the water strider use the surface tension to balance against the gravity, so they can walk on the water surface. And the second picture represents a very interesting phenomenon. It is called the Charrier effect. That means the charriers can self-assembled on the surface of milk, and they will get together and also distributed along the edge of the ball. And people also found the micro and nanoparticles can, at the droplet interface, can make the whole system stable. So based on this, people have developed the Pickering emulsion, and this is widely used in the chemical fields, like the skin carrying products, and also it can be also used as a catalyzer. So these examples show us the interactions between the solid and the liquid surface cannot be ignored, especially at the micro scale. But some underlying physics of this phenomenon, like how the particles can stabilize the interface, is still not fully understood. Moreover, simulating this kind of three-phase flow at the micro scale remains challenging because we need to additionally model the interaction between the particle and the liquid surface. And in this study, we are trying to build up a model to describe this interaction and then develop this kind of lattice Boltzmann model. So about capillary force, so we use a capillary. We introduce a capillary force to describe the interaction between the solid and the liquid surface. Just consider a droplet sitting on a solid substrate, and at the joint point, there are 4 processes at this joint point, and 3 of them, colored in orange, are given by the solid substrate, and this sigma Fs is the joint force of the 3 forces. And according to the second Newton's law, there must be a force with the equivalent value, but given by the liquid forces acting on the solid part. So that force, we call that the capillary force. And capillary force is equal with the surface tension, and it follows the same direction of the interface. But it is not the surface tension, because the surface tension we consider it is acted on at the liquid point, but the capillary force is acted on the contact line of the solid phase. And then for the 3D case, for the spherical particle, so the contact line should be a sealed curved line instead of a point. So the capillary force can be calculated through a line integral along the whole contact line. But in some oh, sorry about that. But in some lattice Boltzmann multi-phase flow models, like the color gradient model and the phase field model, the interfaces are regarded as diffuse interfaces. That means there are several lattices in the width direction of the interface. So the contact line is no longer a sharp sealed curve, but a band. So this line integration of the capillary force should be converted into a area integral. And to deal with that, we introduce equilibrium distribution of the diffuse interface and also the Dirac function. So we distribute the surface tension along the width direction of the diffuse interface, and then we can calculate this capillary force first along the width of first along the direction of the width, interface width, and then along the contact line. And then the line integration of the capillary force can be converted into this area integration. Next, we need to discrete this area integration. So the basic idea comes from the work by Ding and also Dr. Horan in the work in 2020. And we just arrange plenty of monitoring points on the particles, and the integral elements can be converted into the controlled area of each monitoring point following the geometry. And if for the spherical particle, we can build up a spherical coordinate system, and the controlled area of each monitoring point can be easily obtained. And then the whole capillary force along the whole contact line can be obtained by summing up all the values on each monitoring point. And by this, we developed the model of the capillary force, and then based on this, we developed the lattice Boltzmann method to compute this three-phase flow. And for the multi-phase flow of the fluid part, we can use the phase field model or color gradient model. And for the hydrodynamic force about the particles, we can use the immersed boundary or the momentum exchange method. And in this work, we prefer the momentum exchange method. And for both these methods are well developed for several years, so I will skip the detailed implementations, but only focus on the validation cases. And the first validation case is about a droplet adhering to a solid particle. So consider a droplet adhering to a solid particle in the bulk phase, and if there is no perturbation at the initial step, the particle and droplets should be static. And for the particle itself, the Laplace pressure given by the droplet should balance perfectly with the capillary force, so the particle can keep static. Otherwise, it will move with unphysical velocity. And we use this force balance as an analytical solution to check if we can capture the capillary force and also the pressure correctly. And here are the simulation results. So the first figure represents the obtained capillary force under different radius of the particles. So we tried different sizes of particles, and we found when the radius of the particle is larger than 10 lattices, then we can get accurate capillary force. The second picture is about we tried different wettability captures of the particle surface, and we can capture the capillary force accurately when the contact angle ranges from 45 degrees to 135 degrees. And the third one is about the unphysical velocity. As I mentioned, if the capillary force is not captured accurately, then the particle will move with unphysical velocity. And the green line represents the case that we ignored the capillary force model, and then the particle just moves with a large unphysical velocity, as I mentioned. And we also compared with the results captured by the model by Connaughton in 1915, and there is also an obvious unphysical velocity. But in our results, the velocity is very close to zero. And then we increase the surface tension by 10 times. So we increase the surface tension by 10 times. We can find that in our simulation, the unphysical velocity still keeps very close to zero. And this is the second validation. So we simulate a circle droplet sinking into crossing the interface of gas and water, and we can compare these results with experiment observation. And in this snapshots, for the left part of the pictures, these black and white pictures are captured from the experiments, and the right-hand parts are from our simulation. And we can see by this method, the location of the contact line and also the position of the particle can be obtained very accurately. Using this method, we try to simulate the unstable process of liquid column. And for the long liquid column with initial perturbation, it will break up and form a series of small droplets under the surface tension. So it is also called the RP instability, and we just simulate this process to check how the particles at the interface can affect the instability process. I think this should be the animation. Okay, so for these snapshots, we can tell with the particles at the interface, it can delay the breakup of the liquid column. For example, for the short liquid column at the time of 11.2, it has already broken up, but with the particles, it is still not break up yet. And we increase the numbers of particles in this system, and we found that if we add more particles at the interface, the breakup time of the liquid column just will be further delayed. And we also measured the interfacial free energy, the liquid gas and the liquid solid interfacial free energies. And we found during the whole instability process, the liquid gas interfacial free energy changes very dramatically. And that means that part of free energy does the most of the work. And if we put the particles at the interface, then the particle will occupy the interfacial area of the interface, and then the particles can reduce the interfacial free energy of the whole system. And that is we believe that is the reason that the whole system will get more stable. And we also tried the particles with different contact angles. Okay, so we can tell for the slightly hydrophobic particles can make the interface most stable. And we also, accordingly, at that point, the interfacial free tension, interfacial free energy is the lowest. And we also observe the self-assembling of the particles at the interface, and we found that for the hydrophobic particles, they tend to assemble very close to the neck of the deformed column, while for the hydrophilic particles, they prefer to get together away from the necks. And this is because for the hydrophobic particles, they mainly, for the hydrophilic particles, they mainly immerse in the liquid column, and and driven by the pressure gradient, they tend to move away from the necks. But however, for the hydrophobic particles, they tend to get together near the necks due to the attraction of the low pressure zone outside of the liquid column. And this direction is opposite with the inner flow of the liquid column, and this self-assembling can further delay the breakup of the liquid column. And then we can come to the summary. So we developed a gas liquid solid three-phase flow with capillary force to model the interaction between the solid phase and the liquid surface. And then we use this method to study the instability of the liquid column with the particles at the interface. Thank you for listening. Yeah, any questions?
So in your images, it looked like you arranged the particles in a relatively regular pattern on the column.
Actually, this is.
My question is basically, if you try like random arrangements, would that change things? Because it looks like everything stays relatively symmetric, which is probably a result of that regular placement. And things might change if the particles are positioned more randomly on the surface.
Okay, thank you for the question. So I believe so. So because I'm going to try to add as many particles as I can. So I try this symmetric. But if I do asymmetric, I think, of course, the results will be asymmetric. But I think the particles can also, reduce the interfacial free energy, and I guess it will delay the breakup. But I think you are right. Yeah.
What like real or experimental situation could this model mimic? What would be the experimental realization? Yeah. Or possible applications by another liquids?
Okay, so for the application, I think the Pickering emulsion is one of the applications. So people just add nano and micro particles at the interface of the droplet. So the droplet can be stable, and they cannot immerse with each other or just break up. So we can have very stable and regular sized small droplets, and these droplets can be used in like chemical reactions or some other things. Yeah, and also for the small solid like the insects, like the strider on the water. So also we can imagine if we put a coin quietly at the surface of the water, it can flow on the surface and even with a larger density. So I think there are plenty of applications in also the daily life and also industry applications. Yeah.
Well,
Thank you. Thanks a lot. Yeah, I think there's something wrong with the slides.
Press once or more. Just one. Yeah, I saw it, but I don't know. Stimmt das so? Okay.
With a talk titled Incipient Motion at Finite Reynolds Number.
So can we plug in? Really? Oh, come on, guys. Yes. Okay. Can I go to? But
You want to just use it for pointing? Otherwise, there's also a stick here.
yeah, I got it. I got it. Okay. Also, warm welcome from my side, or should I run? Oh, Gott sei Dank. Also warm welcome from my side. My name is Dominik Geier. I'm from the Helmholtz Institute, and I will talk about in-CP motion. I will arise the question when particles start moving or rolling stones. How I will do this? I will first do a slightly physical notion, give you the physical notion. Then I will show you the setup. Afterwards, we will get our hands dirty. We will go to the fluid in the particle solver, how to model a rolling particle, and especially what my part was about is about friction. So I will go into details of the quantum struct spring. And of course, I will show you some multi-scale simulations about shield number and the influence of friction. I really enjoy my topic because when you think about in-CP motion, you can always think about sitting on the beach, see the waves, and then ask the question when the rolling stones or when the sand is moving. And this is, of course, one application. And it also appears whenever a sedimentation or erosion process is coming. So at each river, at each beach, at each sea, and so on. It also appears when cell detaches. And of course, we have also some industrial processes. For example, cleaning surfaces or fluid transport in pipelines. There is also some dirt in pipelines, and you can arise the question, when do the dirt start moving out of the pipeline? Okay, why is this problem a little bit more difficult? Because we are in fluid dynamics, and we have to think about rigid bodies. So really rigid body means we have a force and a torque balance. And on top of this, we consider resting particles, but it's not so natural for fluid dynamics. Okay. Unfortunately, I think the movie will not work. But this is my setup. You see here a quadratic arrangement of spheres, and you see on top of the substrate two spheres. And when the particle starts moving, depends on the shear flow. And in the following, I will consider this on the experimental side and also on the simulation side. And yeah, I think the setup is quite clear. Quadratic arrangement of spheres, I consider a complex substrate. And I have one bead on top of the substrate. So this is a combination of two simulations. And in the following, I will only have put one bead on top of the substrate and the bead move. Okay, do my model, how we implement rolling particle on over the substrate. Of course, I use lattice Boltzmann, except also I will standard DQ 9 letters, the BGK operator. Special to my case is I use Suhi boundary conditions, which was implemented by Jens Harting and Martin Hecht for the Suhi case to generate a shear flow. Also we just have a simple shear flow generated by the Suhi boundary conditions. We have the particles coupled by the monumental exchange coupling by lead. And we implemented a Cantal stack spring to implement the friction between the particles. And as I already told you about the substrate is uniformed, so the particle radius of the substrate and the moving particle is the same, and they, as you see before, are quadratic arranged. Okay, to give you the physical notion behind this, you have when you want to model friction, you have two major ingredients. The first one is the normal force, and this is really the physical notion when you plug an object on a substrate, and you give a tangential force, the object will rest until the tangential force is so high that the object will moving. And this depends on the Coulomb force and also on the surface of the bed. What is important, it also matters how strong is the normal force on the object. You can think about when you want to open a bottle, you put a normal force, then the friction between your hand and the bottle is strong enough, and then you can move it. And what you can see here is the tangential force increasing. And you see here different normal forces. Also the Coulomb law say you have a threshold defined by the normal force to get the friction force out. So for the complete tangential force, I have a linear increase of the friction force until the normal force is not strong enough, and then the particle starts moving. So this is one part, the normal force, which is important. And the second part is the relative velocity. When you have two particles rotating or moving each other, you can calculate the relative velocity, of course, by the tangential velocities and also by the rotation velocities. So these are the two major physical increments for a model. And in the following, I will show you how this is implemented in my source code. So this is the Cantal stack spring. As I talked before, the main part is the relative velocity. And you can see here on the top, we take the relative velocity, calculate the tangential part of the relative velocity. And this is the basis of our Cantal stack spring. Then the most important stuff, you have each time when you move your particle, you have to do a projection in the new tangential frame. This took a lot of time to see this, and in most of the literature, it's not written there. But otherwise, the Cantal stack spring is not implemented in a correct way. So the first step was tangential part, calculate the tangential part of the relative velocity. The second step is the projection in the tangential frame. That's quite simple vector analysis. And now we calculate a so-called test force, which is the Cantal stack spring from before, multiplied by a constant. And then we apply the Coulomb law, which I showed you before. And you have here, again, the normal force. You have overlap of the particle, and you have the friction coefficient, which is quite known to most of the engineers. And now we can decide it again, the two states. One state is the static state, and one state is the moving object. And when I'm below this threshold, I apply the static state. And when I am in the moving state, I'm here, and then I apply this update rule. And yeah, that's it. And that's how I implemented the Cantal stack spring into my model. Question to this? What we will consider is the Shields number. And the Shields number is derived from a torque balance. That means we have the torque from the gravity on my resting particle, which goes in y direction. And we have the torque from the fluid, which is applied on the surface. And we have a torque balance. So the particle rests in the gap. In the following, we consider the Shields number, which is derived from the torque balance just by dividing. also bring on the other side, lever arms on the left side, force on the right side, and then you can have here the sheets number, which fully describe my system. What was thought so far? We showed that this sheets number not fully describes the system. We have also the thing about the friction between the substrate. And obviously, when I increase the shear rate, there is a certain point when the particle starts moving. And this is the so-called critical sheets number. And this is simply done by increasing the shear flow, by increasing the velocity. Obviously, we match to the experiments, as you can see here, for a different gap distance. The critical sheets number. You have here the experimental data from topic, and you have here also our simulation data. And obviously, we match the experiments, otherwise I would not send here. And you can see we match the experiments quite good. And what we showed was that when we tune the friction coefficient, which I showed you on the slide before, that is tuning the sheets number. So the scientific question was, has friction an influence to the critical sheets number? And I clearly can show yes. To come to my conclusion, I showed you in CP motion, which was torque balance on a single particle. Derived from this, you can have the critical sheets number. Then 2 increments of the friction. You have the normal force on the object, and you have the relative force, relative velocity between the objects. I did NSCOC simulation, or source code is NSCOC. I used the lead coupling and the Cantal stack spring. And you can see here the setup. And what I showed you was the friction between the influence of the friction to the critical sheets number. To the end, I want to say thank you to Jens Harting and Rasim Wirschem to enable this project, to my daily supervisor, Ottman. Simon is building up the experiments. Johannes give me technical support, and Paolo Margaretti give me theoretical support. Thank you for your attention. Yeah.
Momentum exchange is of course not Galilei invariant. If you consider using the Galilei invariant momentum exchange, or are you not aware of this problem?
I'm aware of this problem, but somehow I have to stick what is implemented, and the lead coupling was implemented. So of course, yeah.
Okay. You think that code, and in this code there is these things are implemented.
Yeah. We can also think about, we also think about to use item coupling in the next step, but the first step was to get the friction model in it. You're welcome. Thanks. Yeah.
Didn't quite get. Do you actually let the particles to overlap, or do you have some sort of lubrication force?
Also, I have lubrication on, like Lead suggested. The particle overlap in amount of, when my particle radius is diameter is 14, I have an overlap of 0.01 just to get the potentials on. Also, it's not a real overlap, and it's really no. The grid size, the grid discretization is much bigger than the overlap. So I have 1 lattice unit, and I have radius of 7 lattice units. My overlap is 0.01.
Did you say something about mass conservation?
By lead coupling,
Because in a sense, your particles occupy slightly different value in your simulation, right? Because of your overlap. That's what I'm confused.
no, I think you missed the point with the overlap. The overlap is, I can then make the potential cutoff a little bit higher, and then there would be no overlap to the fluid. And yeah, okay, thanks. Yeah.
So, yes, the friction forces right at the touching points of the particle or at the mass center. And can this kind of friction cause another torque?
the friction force is applied on the contact points. And you have to take care, you have 4 contact points. And it's to prevent the particle from rotating in the gap. Because we had this in the simulation, that we apply the shear flow, and the particle was rotating here and not moving over the substrate.
So the torque by the friction.
You have 2 parts. One part is the force on the center, which you're asking for, and one part is the force on the surface. And the surface is a torque. And I apply here the torque. Also without force on the center. Yep.
And do you think that it would change the results a lot if you included also the friction of the rotational movement, like the friction torque?
Other way around. I implement the counter-struck friction to have no movement of the particle, because when I plug it in 2D, my particle is rotating, and in the simulation I have no friction beforehand. So it's just rotating but not moving over the hill.
Yeah, but this is due to the relative tangential velocity of one sphere and the other.
I
mean,
yeah.
the friction is induced by the fact that when the object is rotating another, the reaction force from the ground is not directly crossing through the center of mass of the upper object, but is a little bit offset. So it also like creates this friction torque, but it's not related to the.
You missed the model. We have a fluid flow, who give a force on the particle, and then I have 2 possibilities. One, my particle can rotate in the gap, and one, it can move over the gap. But this rotation in the gap is unphysical.
Yes.
And then, okay, we have to decide, okay, it's unphysical, but what would we do? Okay, we introduce a friction. And this friction is always in the tangential plane, and it's always from the center to the center of the sphere. So there is no difference between. Do you get it, or?
Yeah, I understand. We can discuss.
Okay, thanks. Yep.
By taking the spring is out to obtain rolling. Did you try rolling first or putting on the structure? So did you try the rolling by sphere?
So on a plane surface, we not have tried. I suggested to the experimentators that they should plug the sphere so we can compare with it. But we have this experiment, so I can do it. But I compare it now with the experimental results. So I have just on a complex substrate. But I would also do it as a simple case. Thanks for the question.
One last
Mhm.
So with the math, we guarantee that solution of math.
No, like coupling is intrinsic, not mass conservation.
I think for a single component, you can.
Well, yeah. Ach so, Quatsch. Yeah, sorry, my mistake. Yeah. You take the momentum from the fluid on the particle and back, so it's momentum conservation. And mass conservation you can do. It's how you generate a new fluid. How you generate a fluid node. So when the particle is moving over a lattice point which is not occupied anymore, we do the average about the mass of the fluid nodes. But you can also add. You can also say, okay, I delete this fluid node, memory the mass, and plug it again in. So I would say in my case, it's not completely mass conserved, but it should not matter because it's. Yeah.
And at the same time, you're releasing some on the other side.
Yeah, I totally agree, but you can have the case. As you can.
Some weak distribution, yeah. Okay, but it's It would not be intrinsically completely mass conserving, but I don't know why you asked this question. It doesn't, because it doesn't, I believe it wouldn't matter.
Yeah,
In most applications. Yeah.
I also agree it would not matter, and you have to consider local mass on the particle. So you can have one disk gas, and then we do the average of the local mass. So it's not.
The post processing and they also do the same thing.
Yeah, and also on.
No, well, it's like.
Okay, works.
Yeah. Awesome.
Try putting this on and behind the neck over the ear. And this goes.
Okay.
So we're gonna have a talk by Fabio Guglietta with the title
It's not working, I guess.
Red Blood Cell Dynamics and Realistic Independent Blood Flows, the Effect of Membrane Viscosity.
Okay, no, it works now. Okay, yeah, thank you. Yes, I am Fabio Guglietta from the University of Ron Tor Vergata, and today I will talk about